Welcome back, chemists. In this lesson, we're going to talk about how we identify different chemical substances using what's called mass spectrometry. Mass spectrometry is a technique that lets chemists essentially weigh molecules, not by using a balance, but by detecting ionized particles using a special type of instrument. This is a much more modern technique compared to the physical changes and chemical tests that we talked about recently. Only used really in the last 50 years or so by chemists everywhere, and still used today in a variety of ways. The way it works is, first of all, if you have a sample, samples are ionized. That means they are hit with an electron beam and they actually shove an electron out of it. So it loses an electron from the molecule, creating a charged sample, a molecular ion it's called. Secondly, these charged particles, these ions, pass through a magnetic field. Once the species is charged, it will be deflected by a magnetic field at different distances based on what they weigh. So different sized ions deflect differently. So off to the right I have a schematic of what that all means. Here we have a picture of a typical mass spectrometer. It can sit on most desktops and is attached to its own type of computer. And a chemist will inject an amount of their sample into the mass spectrometer, and a special electron beam ionizes it. It passes through a magnetic field, and then different sized ions are detected differently based on their masses, with more heavier ions deflecting less and lighter ions deflecting more. Less weighing things will be affected by the magnetic field more strongly. So, and what this does is it gives chemists the molar mass of various compounds. So let's say we have a little matching problem to do, and we have in front of us 4 different organic compounds, and we need to figure out which spectrum from these 4 below go with those 4 compounds. Just to label them, I'm going to write what functional group is present in each one. The first one is an example of what's called an amide, followed by the next one is an example of an ester. This is called a nitrile. And then on the end here we have a ketone. You don't need to know those functional groups yet, but you might recognize 1 or 2 of those words from your sophomore chemistry class when you learned about organic chemistry, and we're going to do a little bit more of that later in the year. I want you to notice that the structures are primarily composed of the same 4 elements, no matter which one you look at, namely carbon, hydrogen, oxygen, and nitrogen. And in order to figure out the molar mass of each compound, I need to remind myself that the atomic mass of carbon is 12, hydrogen is 1, oxygen is 16, and nitrogen is 14 atomic mass units. So if I look at these molecules, I can figure out the molecular formula, just add up how many of each element there is, and then calculate what the molar mass of each one is. So the first one has 5 carbons. It has 11 hydrogens, 1 nitrogen, and 1 oxygen. And if I add up the total of 5 carbons, so 5 times 12, plus 11 hydrogens, 11 times 1, plus 16 for the oxygen, plus 14 for the nitrogen, I get 101 grams per mole for that amide molecule. And we're going to do that for the other 3. So I want you to hit pause, and I want you to figure out what's the molecular formula and then the molar mass of each of the remaining 3 compounds that you have on your notes there. Okay, so if you figured out the molecular formulas and the molar masses, the second one, the ester, has a formula of C6H12O2, and its molar mass is 116 grams per mole. The nitrile is C7H5N, and its molar mass is 103 grams per mole. And lastly, the ketone is 3 carbons, 6 fluorines, and 1 oxygen. Interestingly, no hydrogen atoms. I go and I look up fluorine's atomic mass, because I didn't just do it in the beginning. Fluorine weighs around 19, so I add that up and I get 166 grams per mole. Now, to identify which one of these molecules goes with which spectrum, it's very easy, because all you have to do is look at the spectrum and find the peak all the way to the right. The peak all the way to the right is called the molecular ion peak. And the molecular ion peak typically corresponds to the molar mass. So 116, that goes with the ester. So this must be the spectrum of the ester molecule, because that's what I see as apparent peak. But what's up with these other peaks that I see at various numbers? If this is just the ester, why are there so many other things? Well, under the conditions of mass spectrometry, not only do you ionize the whole molecule and take away 1 electron, the energy that's used to do that ionization is sufficient that you might break some of the covalent bonds, and you're left with pieces of the molecule. Even if they have very short lifetimes, they're detected by the instrument and they exhibit a molar mass. So the rest of these peaks that we see are fragments in the spectrum. And chemists use those fragments to piece together what the molecule might have looked like. For example, this 101 right there would be the original molecular ion minus 15. If I just do a little arithmetic, 116 minus 15 gives me 101. And a minus 15 could be the loss of 1 carbon and 3 hydrogens, or minus CH3. And if I look back at the structure, that's not unreasonable for me to lose a CH3 group just by breaking a carbon-carbon bond, and that could happen. This large peak, called the base peak at 57, seems to be what's left over if I broke the molecule at this carbon-carbon bond, because 57 is what you get when you add up 4 carbons and 9 hydrogens, and that's exactly what this left half of the molecule looks like. So we can use the fragments to figure out either what was lost or what's left over, and they all show up in a variety of relative abundances. So now I want you to hit pause again and do the same thing for the other 3. Firstly, simply identify what molecule is represented by the mass spec, and then maybe try to identify one reasonable explanation for one of the fragments that are there. Okay, if I scroll over to the second spectrum in the upper right, the parent peak I see is 103. That corresponds to the nitrile. The peak right here at 104 must be due to gaining a hydrogen atom. That can happen under the conditions of the experiment. You can just acidify it, protonate it. You could also lose a single H anywhere. So that would explain that. The 76 is probably what happens after losing, just doing some simple arithmetic, 27 atomic mass units. So that could be the loss of an H and a C and an N, and obviously there's other fragments that one could try to identify as well. Going to the next one in the lower left, the molecular ion peak I see here is 101. That corresponds to the amide that we have up above. And if I look at the 59 base peak here, that could be the loss of 42, which is the loss of 3 carbons and 6 hydrogens. Looks like we might have broken the molecule off to the left somewhere, breaking off this left branch. That must mean the last one, with a molecular ion peak of 166, that must be the ketone. And the 147 peak, the fragment would be a loss of 19. That's exactly 1 fluorine atom. Here at 97, that's a loss of 69, which would be the loss of a carbon and 3 hydrogens. In fact, here is the peak of of 69. So there's the fragment itself as one piece, and here's the other part of it when it's split in two. So there's a variety of fragments that can exist, and these are all useful ways of figuring out what the structure of something is. In this case, we are strictly focusing on looking at the molecular ion peak. That's the most important thing you should take home from this. That gives you the molar mass of the molecule. And that's how we use mass spec to identify what molar masses are. So lastly, let's look at the mass spectrum of elements. Down at the bottom of your notes, I have 3 mass spectra of 3 different elements. So why do I see so many peaks if I'm looking at the mass spec of just a pure element? Why isn't it a single whole number? Well, remember, all elements, virtually all elements, show up as isotopes. So mass spec also shows us the different isotopes and even the relative amounts of those isotopes. And in this case, because it's an element, I'm actually going to look at the lower numbers first instead of the higher ones. You'll see why in a second. Here I have a peak at 35 and 37. If I look at my periodic table, that's pretty close to what I would expect for chlorine's atomic mass. So why do I have 2 peaks for chlorine? Well, we have 2 isotopes. We have chlorine 35, we have chlorine 37. And I can even use this mass spectrum to figure out the abundance of those. If I draw a line connecting those peaks off to the y-axis, it looks like the larger peak of 35 shows up at about 82, and the other one, chlorine 37, shows up at about 27, just filling it in. And I can use those to figure out the percentage of each. So the percent of chlorine 35 is simply how much chlorine 35 I have, 82, divided by the total, 82 plus 27, and then times 100 to make it a percentage. And that gives me 75% chlorine 35. If you do the same thing for chlorine 37, I won't show it, but take my word for it, you get the remainder. You would get 25% of chlorine 37. And what about these peaks off to the right? We never addressed those. Well, remember, chlorine is diatomic. So these show Cl2. These show molecules of chlorines as opposed to individual chlorine atoms. So we're getting peaks that are 2 chlorine atoms together. In this case, 2 chlorine 35s. The lowest peak all the way to the right here would be 2 chlorine 37s, and the middle one must be 1 of each. So this tells us that this is chlorine. It tells us the percentage of each isotope, and then we can go one step further and actually use that to calculate the atomic mass that we expect to see for chlorine. And this is in fact how you get atomic masses. You take these percentages and turn them into a weighted average atomic mass. You simply do that by taking the percentage of each, so 75% of chlorine 35 plus 25% of chlorine 37, and that gives you a weighted average mass of 35.5 grams per mole. And that's almost exactly what we see on most periodic tables. Chlorine is in between 35 and 37, but it's closer to 35 because more of it exists as 35. So I want you to hit pause one more time, and now I want you to try to identify and make sense of the remaining 2 spectrum that you have. What elements are they? What percentages of each isotope exist? And then what's the weighted average atomic mass? Okay, this middle spectrum here, I see a peak at 79 and 81. Checking out my periodic table, that corresponds to bromine. And let's try to interpret the rest of the spectrum. I'm going to do something much simpler to figure out the percentage of each isotope because I can tell that these peaks are at the same height. So this looks like a 50-50 mix of each one. And then off to the right, as we saw with chlorine, bromine is also diatomic, so I see peaks off to the right that make sense for diatomic bromine. And then if I wanted to get an atomic mass Well, it's 50% of bromine 79 plus 50% of bromine 81, and that gives me 80 grams per mole. Keep in mind, no bromine atom weighs 80. They are all 79 and 81, but on average, we say it's 80 because at any given time it's directly in between, because bromine is very unique and that it has a 1-to-1 ratio of the two isotopes. Most elements do not have that. Most elements have an isotope that's much more abundant than all the others. Bromine is such an outlier because of this feature. And lastly, I have the simplest spectrum of the day at the end. This does not look like a diatomic element because the numbers are so small and there's only 2 peaks. This corresponds to boron. And if I line up where these peaks are with the y-axis, they didn't give me any labels off to the left here, but I'll say that this big number is 10, and that would mean that this one down here is maybe like 2.2. So my percentage of boron 10 would be 10 divided by 10 plus 2.2 times 100, and that gives me 82% boron 10. And then the percentage of boron 11 would be the rest, which is 18% boron 11. And I can use that to calculate the atomic mass, which is 82% of boron 11. Oh, whoops, I have that backwards. My bad. The first one was boron 10, and the first one was boron 11, and the second one was boron 10. That makes more sense. So let's just fix that. 82% boron 10, and 18% boron. Wait a minute. Here we are. 82% boron 11, 18% boron 10. Yep, that's right. That's right. More boron 11. And that gives us 10.8 grams per mole, which is what we see on the periodic table. So, lots of information can come from mass spectrometry. We can use it to identify the molar masses of compounds, and then for individual elements we can get the isotopic abundance, the weighted average atomic mass, and then, in this case, obviously the identity of the element as well. And that's how chemists use mass spectrometry.